All right, well, you want to start? May as well. I feel bad interrupting your silence. You all seem so peaceful. I'm conditioned now. At my house, I've learned not to interrupt silence. When I come here, it feels unnatural. Anyway, before we dive into the next chapter, were there any issues from chapter 7 you guys want to talk about? Anything from Wednesday that's hovering over you, bothering you? Mm-hmm. Number 5 and 7.8. Yeah, let's see. So sorry, you said it was 7.8, number 5. Okay. Yeah, so let's at least start this one, just see how it goes. So with any of these, the first thing you gotta do is scurry off to Wolfram and see what it tells you. So if this were an exam and you see something like that, you say, wow, I sure hope it gives me 3 separate eigenvalues, right? I'm hoping it spits out a 5, a 7, a 10, whatever, because then I'm basically done. Now, of course, since this shows up in section 7.8, that probably won't be the case for you. I assume there's some sort of repetition here. Oops, sorry. Okay, so what it's showing you is only 2 eigenvectors. That's bad for you. You agree with that? Like, oh, that means there's got to be some repetition. If it gives you the corresponding eigenvectors, I guess the question is which of these is repeated? It doesn't tell you up front. So any guesses? Which one is repeated? The 2. That's why it's singling it out down here. It's like, hey, 2, something sort of extra happened. So you can spot repetitions like that. I'm not sure if that was your question or not. What was that your question?
Yeah, it was just that.
Oh, okay, yeah. That's how it'll tell you. Yeah. So then your final answer will look like C1, 2 times what? This times d to the 2t plus C2, the extra stuff you got to build, right? And then plus C3 e to the negative t times that guy. Yeah. Okay. So this homework, by the way, won't be due until next Friday because next Wednesday is spring break again. You all know that? Okay. I guess, I don't know, whoever made the schedule thought Easter break's not enough. All right, we need more break. Always more break, right? You people like that, don't you? I don't like it. What am I supposed to do? Sit at home with my kids? I'd rather talk to you people. Okay, so now let's dive into chapter 9. So the point of chapter 9 is to take what we did in chapter 7 and study ecology with it. So by ecology, I just mean some basic like predator-prey models or competing species models. So the class is not going to suddenly turn into a biology class, but we can at least sort of dip our toes in that water, sort of, and do a little bit of ecology, a little bit of biology modeling. Okay, so we're not going to do that today. The competing species model is a 9.4, predator-prey is a 9.5. So we have 2 sections to do before we get there. We're not doing 9.2, we don't need it. We're doing 9.1, 9.3, then we do ecology. So today, what we're going to do is do a section that just gives language to the different types of pictures we saw in chapter 7, because that language will be useful when you start studying things like competing species. Okay, so today's mostly just a vocabulary section. So it's Friday Fun Day in the sense that we get to look at a lot of pretty pictures, and also the section is fairly short. Hopefully it's short anyway, because I'm already sweating like crazy. I don't know about you people, even with that door propped open. All right, so first a little bit of vocabulary. This will be a nice little callback. An equilibrium. You guys remember that from chapter 2? Yeah. We all liked that. I liked it. Okay, so way back in chapter 2, take this with me. Okay, so way back in chapter 2, I think when I'm recording, I need to stop sharing. I don't know though. And way back in chapter 2, we studied things like this. Whatever. We have like a growth rate right here. And then like 1 minus y over a carrying capacity there, y, things like that, right? You guys remember that?
Oh, yeah.
So this was a logistic model here. Okay. Now, of course, you don't need to remember everything now, but what you should remember from doing like the salmon harvesting problems, things like that, that ring a bell. You should remember that at the very least what we had to do was find equilibria and to do something with it. So the first step in these problems is always the same. What was the first step in these problems to find equilibria? Yes, very timid. Yeah. So an equilibrium is a solution that's constant. So is a solution with zero derivative. So the first thing you do is what Jacob said, I thought pretty constant. And what Riley said, very timid. Okay, so Jacob is the predicate. So he put himself out there to be allowed. You did that. And you solved for one. You guys remember doing that? Okay. So that's what an equilibrium was back in chapter 2, a constant solution of the DE. And we know it's constant because we set the derivative equal to 0. That's what a constant is, right? If the function whose derivative is 0. Okay, so now, in this context here, we're solving for x now, bold x, right? So we're trying to find x1 and x2, or x1 and x2 and x3, depending on the dimension. What is an equilibrium solution now, do you think? Yeah, constant solution. It's the same definition. It's just now both components have to be constant. So we actually need this notion kicked up a dimension now in chapter, whatever we're in, chapter 7. Okay, so now an equilibrium solution is just a constant vector x. If you want to fill this in. Like this. Solution x is said to be if x is constant. So we've seen plenty of non-constant solutions. We've seen solutions like this. You know, C1 vector e to the 5t or C2 vector, or whatever. I'm just making it up. We've seen solutions that look like this. They're not constant, right? Does everybody agree with that? So no, you don't want solutions like this. So what I mean by constant here is if you're dealing with 2 dimensions, it would just look like this. Constant, constant. 3 dimensions, you've got constant, constant, constant. That's the kind of thing we're dealing with here. Okay, so let me just ask you, no matter what this matrix A is, so maybe it's 1, 1, 2, 2, I don't know, whatever. No matter what this matrix A is, there's always at least one equilibrium solution. So there's always at least one constant vector. When you substitute it in here, you get something true. Any ideas what that is? Yeah, so you look down here, right? Scan your eyes down there. Right? If you're dealing with a constant 0 vector, right? Top component 0, bottom component 0. The derivative of 0 is 0, right? Anything times 0 is 0. So check. Okay, so all matrices have at least, no matter what the matrix A is, this system has at least one equilibrium. Now it turns out if A is something called invertible, which for us it doesn't really matter what that means. I think we did like a quick drive-by of this back in chapter 7. But basically for most matrices we'll deal with, or for a lot of them, it turns out the only equilibrium solution is 0. And that'll be the case today. So all that to say though, the idea of equilibrium translates, and most of the time we're going to be talking about the 0 vector, which graphically means right at the origin, right? 0, 0. Everybody okay with that? Okay, so here's just a little bit of terminology reminder from chapter 7. The idea of a slope field translates as we've seen. Okay, so recall that a solution is a vector like this, some sort of vector function of time that satisfies this. That's what it means to be a solution. And as we discussed, we get these pictures in the x1, x2 plane. Y'all remember that when you look at a slope field? So you get these sort of like spirally shapes, or I don't know, shapes like this or whatever. So over time, you can watch x1 and x2 change. Such a curve like that's called a trajectory. We use that language, but didn't formally define it. But we did talk about it in chapter 7. So the x1, x2 plane itself, where we're drawing these slope fields, is called the phase plane, if you want some fancy language for it. And if you start drawing a bunch of these curves, that's called a phase portrait. So let me just show you an example of that. Let me get a slope field going. Okay, here's a slope field. Y'all recall looking at these things from chapter 7? X1, X2, like that. So no matter what the initial values of X1 and X2 are, let's say X1 starts at 5 and X2 starts at 8. What's going to happen here? Converge to where? To the origin, right? If they're populations, they'll both die out. Everybody agree with that? They just go to the origin. Anyway, so this is called a, what's my new language? Oh, just a slope field, right? In the phase plane. Now suppose that I started plotting points, like there's a point right there. I guess I have to angle. So here's a point right here. Suppose you then drew a curve that followed the arrows. You draw something like this. Everybody agree with that? That's called a trajectory. So you can do that a bunch of times if you wanted to. You could say, well, what if I started here? If I follow the arrows, I draw a curve like that. It's another trajectory. Everybody okay with that? If you do that enough times, you get what's called a phase portrait. So the phase portrait lives in the phase plane. There's a lot of fancy language around this. But again, neither of these axes is time. X1 axis, X2 axis. So you're watching X1 and X2 track together over time. And if you just fill in enough of these trajectories, you get what's called a phase portrait. So here's an example like that down here. Okay, so for this system here, I think that's what I have on the screen. Yeah, that's what I have on the screen. If you pick a bunch of start points, see how it's picked a bunch of start points? And you watch the flow, that's what they'll do. Those blue curves there are trajectories. So just questions on that language, or is that okay? Okay, so now let's back up a little bit. Here's a system that back in chapter 7, I could ask you to solve it. Everybody agree with that? And then what would you do? Yeah, good. You just do what we've been doing for a week now or whatever. We go to Wolfram. Let's get the information. Well, I guess I want to share this again. Okay, so eigenvalues, -3, -1, 2, -5. Okay, so here's what it spits out. Let me approximate everything. It gives me 2 real eigenvalues, and they're both different, so there's no repetition. Everybody okay with that? And of course, there are 2 eigenvectors with it. So notice, if you were to plot those 2 vectors, let me plot them. I'm just going to draw little arrowheads pointing to those points. Okay, so one of the vectors says if you take 0.3 steps to the right, you have to go up 1. So I'll put a little scale in here. It's like saying this. Is that okay with that? The first vector. And the next one says if you take a step of size -1 point, or a step of size 1.366 to the left, this way, you're also pointing at the 1. So you're pointing at that point. So there are those 2 vectors. Okay with that? So back here in this picture that we have in the handout, There's one of the eigenvectors, there's the other one. You guys see that? And now I'm going to plot those. I'm going to get my slope field back and plot those two vectors. But what I'm going to do is I'm just going to create lines out of them. So I'm going to take the arrows and just stretch them infinitely in both directions. So there's one of the eigenvector lines, and there's the other one. Everybody see that? Now, do you notice what's happening with the behavior here? Things are getting sucked to zero, right? But they're not just getting sucked to zero. Can you describe what's happening here in terms of the eigenvectors? What do you notice? Oh, I just mean like, if you look sort of broadly, right? How are the eigenvector lines interacting with this picture? Yeah, they flow to this line. So basically, this line is acting like an attractor or something. So they flow to this line, and then this line like shunts them down to the origin. Everybody see that? The reason that occurs is because this eigenvector here, if I go back to my information from Wolfram, that eigenvector corresponds to the bigger of the two eigenvalues. So the bigger of the two eigenvalues, its eigenvector will sort of dominate this picture and act like a sink, or act like an attractor. Okay, so all that to say, we already have the idea of a slope field, we already have an idea of flow and so on. It turns out that eigenvectors can sort of tell you how things will flow. So in this case, we don't just know things flow to the origin, we know that this eigenvector of the bigger eigenvalue acts as an attractor, and then that sends things down to the origin. So that's what's happening in this. Sorry, I have too much stuff open. That's what's happening in this picture here. You guys see that? Here's this sort of eigenvector line. Things get sucked to that and then down to the origin. Now, there's a name for pictures like this. This kind of picture is called a stable node. A stable node is what happens when you have two eigenvectors like this, and the dominant one acts as a sink, or as an attractor. So all this section does is it just sort of walks through what kind of pictures you can get like this and gives names to all of them. So it is just purely a vocabulary section. So any picture like this is called a stable node. This, by the way, is not something to memorize. You'll be given a chart with the terminology there. You just have to know to use it. And so, again, a stable node is anything that looks like this. If I were to do things like, you know, take these two eigenvectors and rearrange them, like rotate them or something, you get the same kind of picture. So let me show you something like that. Here's another stable node. Get rid of all these. Okay, here's another stable node. So this system here, I don't know if you can see the coefficients, but now the matrix is 3, -2, 2, -2. So it's a different matrix, but notice the behavior is still basically the same. Here are the two eigenvector lines that Wolfram would give you. And still, you see one of the eigenvector lines acts as an attractor, right? Things are being pulled towards it. So there's another node. So anyway, anytime you have an eigenvector line acting as a dominant attractor like that, that's called a node. Okay, back to the handout. Okay, so you notice the handout terminates pretty quickly, basically because I'm just going to give you a chart that tells you what kind of pictures arise based on what eigenvalue, and that's all the section is. Okay, now the last thing you should ask, I think, or the last thing we should discuss, is I called this thing not just a node, this picture, but a stable node. Does this word sound familiar from previous material? Stability. You guys remember the idea of a stable equilibrium? What did that mean back in chapter 2 or 3 or whatever? Yeah, good. It was like an attractor itself, right? So in that carrying capacity example, the carrying capacity was a stable sink or something, right? Y'all remember that? So if the carrying capacity was 4,000 and I knocked you down to 3,800, you would just go back to 4,000. Remember that? That's what stability means. I can just sort of knock you off of it and then you flow back. So let's look back at the original picture I had. Not this one, but this one. Okay, so the origin here, this is an equilibrium. Do you think it's stable or not? Would you call that thing stable? Yeah, why? It's acting like a sink, you know? And in particular, imagine you're sitting at the origin, and then I come and I shove you off a little bit, right? So now you're right there. What do? You're right back. Everybody see that? So the idea of stability still translates. The idea is just, I mean, it's what you guys are saying, but if I, in particular, if I just push you a little bit off the equilibrium, you'll come back. That's what stability means. Now, by contrast, this picture here was a node, but notice it's qualitatively different kind of node, right? Now, if you're at the origin, and I sort of like kick you off a little bit, right? You go back to the origin. I know, you squirt off somewhere else, right? Off to infinity, I guess. So this is unstable. And that idea was still true. That idea was still true back in chapter 2. Unstable equilibria were if I knocked you off that line a little bit, you just squirted away from it, right? You float away. So all of that concept still translates to chapter 9 or to chapter 7. So this is called stable because it flows to the origin. The picture I just showed you is called unstable. Okay, so now let's look at one more example before processing the chart at the end. So 5, -1, 3, -1. So like before, we get the eigenvalues and eigenvectors. I want to though get them to compare and contrast them to the last one. So take a picture of this in your mind. The last example, we had 2 real different negative eigenvalues. Got all that, right? They were real, different, and negative. Somebody be in charge of remembering all that. Who's the most awake right now in this heat? Evan. Evan's the most awake. All right, so you're in charge of remembering that. So now I'm going to type in this. I'm only awake because I'm standing up here. It's hard to fall asleep standing up. But this heat will certainly weigh on your eyelids. So again, we're almost done. With me up here anyway. Okay, so now, you can get approximate forms. These eigenvalues are real. They're different, but what's different now? One's positive, one's negative. It turns out that kind of difference, that kind of thing will make a difference in the picture. So now if I go to the phase portrait, I think I have that preloaded. Yeah. Whoops. What was it? 5, -1. Yeah, whoops. Come on. Oh, here. Before I type that. Like that. Yeah, this is called a saddle. So basically what's happening is the plane is divided into 4 pieces, like this. The eigenvector line is divided into 4 pieces, and things kind of flow from the least dominant one to the dominant one. So you still have a dominant one that's acting like an attractor, but now the other one's acting like a repeller. That's what a saddle is. Before, the other one wasn't really acting like a repeller. It was just kind of there. But now things are definitely flowing away from this least dominant one, and this least dominant one comes from the negative eigenvalue. The smaller eigenvalue is always the least dominant one, and the bigger one is always the dominant one. Its eigenvector will drive the behavior of the flow here. So anyway, this is not, it looks kind of like a node, but it's not. You get the sort of saddle-looking pictures here. Okay, so the punchline of the section is the type of eigenvalues you have determines what kind of picture you get and what kind of flow behavior there is. So far we've seen a node, so far we've seen a saddle. There are, of course, all sorts of other ways the eigenvalues can be different. So notice we've seen this. Sorry, I guess it won't let me highlight individual rows. We've seen this, right? 2 negative, distinct, real eigenvalues. And we got a stable node. Now, just like back in chapter 2, the book likes to add this adverb of asymptotically. In this chapter, it actually makes some sense to do that. And we'll talk about why when we get to it. But we got a stable node. Then, when we got 2 real guys that were different, but one was positive and one was negative, we got something called a saddle, which is also unstable. The origin is still unstable here, if I bring this picture back up. All right, so if you're at the origin and I knock you off, now you're going to flow like the saddle shape. Everybody see that? You're not going to go back to the origin, so it's unstable. But there are lots of other ways that eigenvalues could shake out. You could have 2 positive real eigenvalues that are different. You could have positive eigenvalues that are real but not different, the same. You could have complex eigenvalues and so on. Every one of these cases will give you a different kind of picture, as we basically already discussed back in chapter 7. So I want to show you a few of these. Okay, so let's pick off, let's just look at, I don't want to do all of these, but let me show you this one maybe. Okay, so you see this picture? Much different, right? Like a spiral. So now if I go to Wolfram and I type in this matrix that I used to get it, so the matrix is 2, -5/2, it looks like, 9/5, -1. Wolfram gives me this. Here are my eigenvalues now, the complex. So as we've already discussed, complex eigenvalues give you the sort of spiral behavior. And so now I scurry back to this table. I'm like, now what's this called? Okay, so I'm complex. And notice they break complex into real and imaginary parts, right? So it turns out if your real part is positive, that'll give you a different kind of picture than if your real part is negative. So my real part here is positive. Okay, so it's telling me when my real part is positive, I get a spiral, but it's unstable. Let's see if that corresponds to the picture I have. Okay, if you're at the origin and I knock you off the origin, where do you go? Not back to the origin, you know, you'll do like this. Up, over, like this. Eventually you'll sort of spiral out of control if you follow those arrows. So it looks like a hurricane or something, right? But you're going away from the origin. This next example in my picture, or my list of pictures here, I just want to show you 2 more examples real quick to show you the complex cases. This is a spiral, but basically the arrowheads are reversed, right? Now if I knock you off the origin, you flow back, right? So this is like what? This is how toilets flush in the northern hemisphere, and this is toilets flushing in the southern hemisphere. That's how you remember the difference. Little exam tip for you. If you're in Australia, this is what toilets will do if you flush them. Yeah, that's what happened. I think anyway. I haven't been there, but I've never been to the southern hemisphere to test out this theory. But I saw a YouTube video on it once. Okay. Yes, I want to show you one more. This one. Okay, so this looks very similar. This looks like a spiral. I want to hand this off to the computer though real quick, the Wolfram, and have it find the eigenvalues. Okay, so the matrix is 1, 2, -5, -1, like that. These are purely imaginary. There's no real parts. So if you go to this chart, it tells you get a center, which notice is not a spiral, it's something else. It still calls it stable though. Okay, so the difference between a spiral and a stable, or in a, what? A spiral and a center is the following. They look kind of the same to the naked eye, but if you were to pick a point here and draw the trajectory, it would go like this, and you'd return where you started to. Trajectories are ellipses now. Everybody see that? It's actually not going to shoot you off to infinity or shoot you into the origin. So if I start right here and I follow the arrows, up, over, down, but there's nothing forcing me like farther away. Everybody see that? So trajectories are ellipses, or sometimes circles, depending. So you follow up, over, back. So such a thing, your book calls stable, because if you're on this orbit right here, maybe, this trajectory, and I knock you off your orbit a little bit, you don't go back to the same orbit. If I agree with that, like if you're doing this, and I knock you over here somewhere, it's not like you go back to that orbit, but you will just fall into another sort of stable elliptical orbit. You don't squirt off to infinity. So that's the difference now between asymptotically stable and stable. Asymptotically stable means if I knock you off the origin, you go back to the origin. Stable means if I knock you off the origin, like here, if I knock you off the origin, you don't go back to the origin, but you also don't squirt off to infinity. So it's like a halfway measure or something. You're sort of like half stable or something. Anyway, these are the kinds of pictures you can get. So this table here is a culmination of the section. So if you go to Moodle, I have a folder here called section 9.1 images. If you want to see all different kinds of these pictures, I have all of them listed here, including some ones that your book doesn't have. So these are all the ones that we'll need for the models we're going to build, but this is actually not an incomplete list here. Among other things, you may notice, well, somebody tell me, what cases are missing here? What could happen that's not listed here in this eigenvalues column? Yeah, if the eigenvalue equals 0, which could happen, it just omits those cases. It doesn't care about them because we won't see them. But I'm a mathematician, so I care about completeness. So I put some of those pictures in here. Where am I? Here. You get what's called a star point. That's what happens if you get an eigenvalue of 0. Anyway, so you can look at all these. The book doesn't have a complete set of pictures. It only has like 3 of these. I'm not sure why it doesn't have a library like this. But if you're curious, like, hey, what does an unstable saddle look like? What's an unstable node? Whatever. Like, there's a picture like that. Unstable node. So you got your eigenvector lines. One of them is acting like a repeller. Like this dominant one's repelling things off. Unstable. Well, I guess I should have said, your book also uses synonymous language. Like, instead of saying node, sometimes it says nodal source. You can pick your favorite. I don't really care. So you can just say unstable node right here, stable node, things like that. Anyway, so there are all the kinds of pictures you can see. Okay, so the punchline moving forward is we need this language to categorize the kinds of behavior we see in ecological models. So it turns out there will be equilibria in those models, but those equilibria won't be the origin necessarily. They'll be like a coexistence equilibrium somewhere else. And you have to ask yourself, is what I'm seeing stable or not? Is it like nodally stable or spirally stable? We'll need that language moving forward. So before we go today, I do want to have you guys, just to make sure you understand what the takeaway of the section is, I want you to try a few of these. Okay, so try maybe like A, B, C. You get the idea after that. So for each of those, I want you to classify the equilibrium at the origin by stability and type. So all I'm saying is, I want you to, not this. Did I close my, I closed it, all right. I want you to get the eigenvalues, classify based off of this, just to make sure you understand the language and visualize what the slope field looks like. It'll take like, I don't know, 5 to 10 minutes to do that. Is everybody okay with that? Just like A, B, and C. You sort of get the point after like A and B.
Good.